Hey, and welcome to The Explainer. Today we're going to tackle a core idea in math that's all about connections, the mathematical relation. It might sound kind of formal, but I promise you use the logic behind it literally all the time.
Think about it. How do you actually take an idea like is taller than, or is a sibling of, or is in the same class as, and pin it down with the pure, hard language of mathematics? Well, that's exactly the puzzle we're going to solve.
All right, let's get right into it. To really get what a relation is, we have to start with the official definition. But hey, don't let the math speak freak you out, because the idea itself is actually, surprisingly simple.
Okay, that sounds pretty dense, right? A subset of the Cartesian product. But let's just translate that. All it really means is that a relation is just a specific list of chosen pairs. You've got two groups of things, set A and set B. A relation is just you picking out the specific pairs that follow some rule you care about. That's it. It's like a VIP list for pairs.
And this is the shorthand you'll see everywhere. If you see XY, it's just the cool, quick way of saying, hey, the pair XY made the cut. It's on our list. It means our rule connects X to Y. Simple as that.
So theory is one thing, but let's actually see this thing work. This is where it all starts to click and, honestly, where it gets fun.
Okay, here's our first mission. We've got set A and set B. The rule we have to follow, our connecting principle, is X is less than or equal to Y. So our job is to build the relation R by finding every single pair that makes this rule true.
So step one, we just forget the rule for a second and make every single possible pair we can. This complete list of every combination is what we call the Cartesian product. So we take the 1 from set A and we pair it with both 3 and 2 from set B. Then we grab the 4 from set A, do the exact same thing. We just keep going like that for every number in A until we've got all 8 of these possible pairs lined up.
And now we filter. It's like a game of keep or discard. We go through our list pair by pair. Is 1 less than or equal to 3? Yep, keep it. How about 4 less than or equal to 3? Nope, that one's out. We just do that for every single pair. And the ones that survive, the ones that pass our test, well, that's our final relation, R. And that's the big takeaway here. The relation is just a hand-picked subset of all the possibilities we started with.
All right, let's do a quick fire round to make sure this is locked in. We've got new sets, C and D, and a brand new rule. X divides Y. That's just a fancy way of saying Y is a multiple of X without any remainder.
Okay, first the Cartesian product. That gives us 4 possibilities. Now let's apply our new rule. Does 2 divide 5? No. Does 2 divide 6? Yep, it does. We keep it. Does 3 divide 5? No way. Does 3 divide 6? Yes, it does. We keep that one too. And boom, there's our final relation. R is just those 2 pairs. See? Same process, just a different rule.
Okay, so now that we know what a relation is, we can start to describe its personality, its different behaviors. We can actually test relations for specific properties, almost like their character traits. And the first one we're going to look at is what I like to call the mirror test.
So the formal name for this is the reflexive property. A relation is reflexive if every single element in the set relates to itself. So think of each number looking in a mirror. For the whole thing to pass the test, the pair x, x has to be in our relation for every single element, no exceptions allowed.
So, I've got a challenge for you. Our set A is 1, 2, 3, 4. Now here the pairs in our relation are, we've got 1, 1, 1, 2, 2, 3, 3, 3, and 4, 4. So looking at that evidence, what do you think? Does this relation pass the mirror test? Is it reflexive? Let's run the checklist, kind of like we're detectives. For the number 1, do we have the pair 1, 1 in our relation? Yes, we do. Check. For 3, we see 3, 3. Good. For 4, we see 4, 4. Great. But hold on. Look at the number 2. We search our list of pairs for 2, 2, and it's just not there. It's missing. That's our big clue.
And that's the whole ball game, because we found just one element, the number 2, that doesn't relate back to itself. The entire relation fails the test. It is not reflexive. Remember, the rule says for every element. One failure and the whole thing comes down.
All right, on to our next property check. You'll start to see how these build on each other. This one is all about how things connect, so I call it the chain link test.
This property is called transitivity, and the logic is really intuitive. If you have a path to get from point A to point B, and then another path that takes you from B to C, then for this relation to be transitive, there has to be a shortcut, a direct path from A straight to C. If any chain is missing that final link, the property is broken.
Okay, time for another investigation. Let's say our relation R has these three pairs, 1, 3, 3, 2, and 2, 1. We can definitely see a chain forming here, right? A path from 1 to 3 to 2 to 1. But is it a complete chain according to the rule? Is it transitive?
Let's trace just one of these chains. Our relation has a link from 1 to 3, that's our AB. It also has a link from 3 to 2, that's our BC. So the transitive property demands that a direct link from 1 to 2, our AC, must also be in the list. But if you look at our evidence, the pair 1, 2 is nowhere to be found. It's missing.
And there's our verdict. We found a broken chain. That shortcut from 1 to 2 that the rule required, it doesn't exist in our relation. And because of that one missing link, this relation is not transitive.
Okay, for our last property check, we're going to look at a few different flavors of symmetry. Now, this is where it can get a little bit confusing, but thinking of it as a two-way street test really helps make it all clear.
Okay, let's break this down. On the left, you have symmetric. This one's easy. It just means every road is a two-way street. If you have a path from A to B, you must have a path from B back to A. Now on the right, you have antisymmetric. Think of this as a system of one-way streets. A path from A to B is totally fine. But if you also have a path from B back to A, that's a problem, unless A and B were the same thing to begin with. So a loop on one spot is okay, but a true two-way road between two different spots is forbidden.
And there's one more, even stricter level, asymmetric. This is the ultimate one-way street. If you have a path from A to B, a return path is absolutely positively forbidden. No exceptions, not even for loops. So to recap, symmetric demands two-way streets. Antisymmetric allows only one-way streets between different points. And asymmetric says no return trips, ever, period.
So let's tie it all together with this. The relation is less than, that we all know. Well, it's transitive, it's a chain link, and it's also asymmetric, a strict one-way street. So my last question for you is this. What other relationships from your actual life share those exact two properties? Think about is an ancestor of, or maybe a reports to structure in a company. Once you start looking for this stuff, you'll see this kind of mathematical logic is absolutely everywhere.